Hello guys, we are doing 2.2, which is about atomic structure and the periodic table on today's video. Alright, so this is a bit longer than the previous one, but let's get to it without further ado. Okay, let's talk atomic structure. Atomic structure. All substances are made out of atoms, right? These small particles called atoms. But what are they? What are atoms made up of exactly? So that's basically what this atomic structure really is about. I think this is a very basic one, but it's really important to recall it, and it's part of your syllabus in GCSE as well. So, don't mind my circle drawing skills. This is supposed to be some sort of a circle. There we go. That's alright. And then there's also, let me actually draw this one with a different color, okay? An atom has these ones. Sorry, what color do you want to use? Light pink. These are called electronic shells. And in the electronic shells, we have electrons. All these little pink ones that you see here are electrons. Alright? So that is an electron. An electron is a negatively charged particle we're going to look more into this in a little bit. Alright? And then here we have the protons. And we also have the neutrons. But in general, this is your nucleus, and the nucleus is what contains this proton and neutron. It contains your proton and your neutron. And your neutron is uncharged particle. It's not positive and it's not negative as well. And lastly, we obviously have the proton, which is a positively charged particle. Alright? So, in the first syllabus point, they want you to describe the structure of your central nucleus with your neutrons and protons surrounded by your electrons in the electronic shells. Alright? Now, there's this table that I'm pretty sure you all have seen in multiple times, and let me just draw that roughly. Okay, so you have particles here. Particles, relative charge, and relative mass. Alright, so you basically need to know the quantitative of these particles. What are they? Alright, the particle, relative mass, as well as the charge of these particles. Alright, so we know the three particles that we've just discussed previously are our protons, neutrons, and electrons. The relative mass of a proton and a neutron is approximately 1. However, electron is the most smallest subatomic particle, and it's approximately 1 out of 1840. It varies 1 out of 1837, 1840, but this is usually around the area, okay? And we know protons have a positive charge of a +1, neutrons are not charged, and last but not least, electrons are negatively charged. So you just need to revise and remember this table. There's not a lot to remember really, so it's going to be pretty simple. That is on the first one and the second units. Points done. So an atom in the periodic, an element, sorry, in a periodic table, can have a proton number as well as an atomic number. Sorry, as well as mass number. A proton number, another name of it is atomic number. So these can be interchangeably used to define the same thing. So what are they, and what exactly does it tell us? Proton number just tells us the number of protons in the nucleus of an atom. Okay, now if I go back to my periodic table over here, we can see clearly all these elements are arranged with the proton number. Here, potassium has 19 proton numbers, calcium has 20 proton numbers. So in the periodic table, the elements are arranged in the increasing order of the proton number or atomic number. So mass number, also known as nucleon number, or nucleon number is basically the number. Okay, we'll look into that, no worries. Word you can use is nucleon number. All right. So what this is basically the total number of protons and neutrons in the nucleus of an atom. Now, if I go back to my little image that I drew, it's not very accurate in terms of the electrons present, but let's just look at this. If I'm asked to write the proton number of this certain element, all right, I know there is 1, 2, 3 positive charge, so my proton number here would be 3, looking at this example. And if I'm asked my nuclear number, or the mass number, I have 1, 2, 3 protons and 1, 2, 3 neutrons. So that's my proton number plus my neutron number. So that's 3 proton and 3 neutron, which gives me a total of 6. So this atom has 3 proton number and 6 nuclear number. So that's basically what they want you to do. You need to be able to define them and use them, okay, in your definition, especially when you're trying to define isotopes, all right? Now, and the fifth point is to determine the electronic configuration of all the elements and the ions from proton number 1 all the way to 20. So that's from hydrogen all the way to calcium. You need to be able to determine the proton number, all right? Now let's do a little bit basic of how do you configure, how do you do electronic configuration, all right? So electronic configuration basically is the arrangement of electrons in the electronic shells. Okay, this is not part of the syllabus, but as a background to understand exactly, there are 4 shells that you usually use: K, L, M, and N. And basically, you can just call it first one, second one, third one, and fourth one. All right? So, configure and distribute the amount of electrons you have. You need to be able to know how much each shell can contain. All right? Your first shell, K, is quite small. It can only contain 2 electrons. Your L shell can contain 8 electrons. Your M shell can contain 8 electrons. And you don't really go past N, but your N can also contain 8 electrons. Alright? So, if I get my element, for example, let's take boron. Oh my god, bit of a wrong color on a white. Boron with a proton number of 5. Alright? So one thing I'd like to note, I'm going to write it in red. Proton number is equal to electron number. And this only applies if it's an atom. So unless you have an ion, it's an ion. All right, your ion means you've lost electrons or you've gained electrons, so that in that sense you won't have same number of electron and proton number. All right, so let me just use my green highlighter to kind of draw a box around it. It's an important thing to remember. Sorry for not mentioning it earlier. Let's say boron with 5 proton number. It's an atom, so we already know B with 5 will also have 5 electron numbers, right? So, if you are told to write the configuration of this, because I know my first shell has 2 electrons, I'm gonna write 2, comma. Now I'm left with 3 electrons, and my L shell can only hold 8 electrons, but I only have 3 left, so I just have to put the 3 over here. Nothing to worry about. This is quite a simple one to do. Now let me go back. Let's take a little harder one. Let's take aluminum just down here with a proton number of 13. It's an element, it's an atom, not an ion. So it will also mean it will have a proton number, because it has a proton number of 13. It would have an electron number of 13 as well. So 13 here. So if I were to configure this electronic configuration, that would be 2. And then 13 minus 2. Okay, this will come off to you very easy once you do it very often, all right? So 13 minus 2 here is 11. Sorry, how much is that? My math is a bit behind, sorry. 13 minus 2 is 11, all right? So, I cannot put 11 right here. No. Because the L shell can only contain 8 electrons. So I need to do 2, then I put my 8 electrons, right? So that means I've configured the 10 electrons out of the 13. Now I can simply put the 3 here, so I have a nicely configured configuration of aluminum atom. All right, so you need to always look at how much each shell contains. Apart from your first shell, your second shell and your third shell and so on can only contain 8 electrons, and that's what you need to know at your level. All right, now let's take the maximum. Okay, that is your calcium. Ca has a proton number of 20. That also means an electron number of 20. All right, so if we want to configure calcium right here, what do you want to use? Orange maybe? All right, so I'm going to put 2 here. So out of the 20 electrons, you need to do this like subtraction in a separate like place, a little subtraction, or use your calculator if you have to. I've only used 2 electrons from my 20. If I subtract, oh my god, I still have 18 to configure. So because my second shell can only contain 8 electrons, I'm going to put 8 here. But I still need, out of the 20, the 10 I have configured, I still need to distribute this 10 electrons yet again. Not done yet, all right? So, I can't put my 10 here like this. Absolutely not. So what is the right way to do? We've come from 2 to 8, but this 10, remember your third shell cannot contain more than 8 electrons. So third shell will also contain 8 electrons. So if I count 2 plus 8, which is 10, 10 plus 18, which is 20. So I just put my 2 here. So this is the correct configuration of your calcium atom or element, basically. So that's how you basically do electronic configuration. Okay, If you guys need more video and an in-depth video of this, then I will absolutely be down to do so. All right, there we go. We're done. Now I want to come back. Now that we know all these things about our atoms, our protons, electrons, I want to go back to how an element is represented in the periodic table and what exactly does it tell us. All right, so if I could go maybe here. All right, so if I put my X here, little X right there, and I'm going to put my A here and my Z here. We're going to look at what this means very soon. I want to change my color into something interesting. Let me just maybe that red. Okay, so A here is my mass number. Sorry, let me just give it space a little bit. Mass number. What did we say about what my mass number is? Mass number is the number of protons plus neutrons in the nucleus of the atom. All right? So it's basically tends to be the bigger number. Okay, we're going to look back at the periodic table in just a bit to really understand what exactly is happening. And the Z here is your atomic number or your proton number, atomic number. And this is just basically the number of protons in the nucleus of an atom. And your Z basically is just your chemical symbol of your element. So let's go back to my periodic table in order to see what exactly this representation is and how they show it. Now, in some periodic tables, they could switch up the position of your atomic number and your mass number. And in here, it is very similar, okay? Let's take cobalt here. Okay, so they wrote it as CO2759. Always know the smaller number is your mass number, and another, like a symbol to represent mass number, is your A. Okay, so the smaller number, get my pen, smaller number is your Z, also known as your atomic number or your proton number. So they could switch it up in periodic tables, but you need to look at it and be able to recognize what is what here. All right. Here they've also given you your key, the same exact thing. You have your atomic symbol, your A, which is your atomic mass number, relative atomic mass, same thing, and atomic number or proton number. Okay, you can always look at your key and try to understand what and how your atom or your element is being represented as. All right, so let's go to the last point that is concerning your group 8, sorry. Your noble gases, what are they? What makes them different from all the different atoms that we are being given that we know of, all right? So, let's go periodic table. There we go. Group 8 that we call them are these last ones. The last ones here. I'm actually going to use like a bit of a brighter color. Red maybe? Yes, there we go. So all these, your krypton, your radon, your helium, your neon, all these are your group 8 elements. So what is actually different about them? Why do we talk about them quite a lot? Group 8 elements are different, and the reason they're different is, and they're called noble gases, is because they are unreactive. Okay, let me just I would like to take this a bit up here so that I have space to do a little explaining or not. Group 8 elements. They are very much unreactive. when you talk about different reactions in chemistry, you will not talk about group 8 because they do not want to react. Okay? And this is because they have a full outer shell. Alright? Now, we did see to have a full outer shells, you need to have 8 electrons on the outer shell and the outer shell. Let me just move this a bit up so I have space. So they have full electrons, 8 electrons on the outer shell. Whether it's their first shell, their second shell, their third shell, they'll have 8 electrons on the outer shell. Or we know the exception of helium because it only has 2 and the 2 electrons. It's helium. Let me just write that down. Helium will have 2 electrons. Okay, now a nice little reminder, if you can't recall, is your outer shell. I'm going to write this in red. I'm going to write the little important reminders in red, okay? So your outer shell electrons are actually known as your valence electrons. So you don't always have to use outer shell electrons. You can just call them valence electrons, which is basically the same thing, really. Okay, let's go back to helium and all the group 8 elements, the noble gases. Okay, you know helium has 2 electrons, and in order for your first shell to be full, you're gonna have 2 electrons. So it technically fits and cuts the deal. So they all have a full outer shell. But what exactly does it mean? That's kind of like a example. Let's take a nice little example as a married couple. Okay, a married couple will not need any. Okay, sorry for the drawing. Won't need anybody else, right? Generally, they don't want anybody else. They're already married. They have everything they need. So they have everything they need. So don't need to go like to places. They don't want to go and get to know people, to go find new people. So that's kind of a nice little example you can use to remember the noble gases. They're married. It's cut the deal. The ring is there. They don't want anything because they have everything they need. Lucky for them, unlike other elements in the periodic table that have to react. Okay, so basically in the syllabus. Sorry, let me go back to the correct one. They want you to know that the group 8 noble gases have full outer shell, okay? And the number of outer shell electrons is equal to the group number in group 1 to 5. What exactly does this mean? If we look here, all the atoms in group 1 will have an outer shell or a valence electron of 1. Same for the second one, same for the third one, same for the fourth one, and so on. So if I want to put that into words, I'm also gonna write that in red because it's quite crucial, no? Group number determines the number of valence electron of elements, right? Now let's actually try to use an example here. Let's use beryllium, magnesium, and calcium in this example. So beryllium with 4, magnesium with 12, calcium with 20. I'm trying to remember that so quick so I don't have to go back. So beryllium, magnesium, calcium. Beryllium with 4, magnesium 12, calcium 20. Let's try to do electronic configuration of all of these first, alright, before we kind of come to a conclusion. Maybe it could be wrong. Let's see, alright? So I bring out my marker here, perfect. So, beryllium. Remember, first shell should only contain 2. Second shell can only contain up to 8 electrons, but beryllium only has 2 left, so that's basically 2, 2. Perfect. Now magnesium would have 2 on its first one. Out of the 12, we've used 2, so that's 10 electrons left. But your second shell can only contain 8 electrons, remember? So we add 8. Then out of all of these, there's 2 more electrons left. There we go. Calcium. We already did calcium earlier. It's 2 the first one, 8, 8. 2. You can go a little bit back from the video to recall what exactly and how exactly calcium is configured. But that's basically it. What do we notice in here? What do we notice? Beryllium has a valence shell electron of 2. Magnesium has a valence electron of 2. Calcium has a valence electron of 2. They all have a valence electron of 2 and are all group 2 elements, right? Sorry. Group 2 elements. So have we proved this theory correct? We can take any elements and we can try it. This theory will stand true. So there we go. Group number determines the number of valence electrons of elements. Another thing you want to look at is what does period number determine? Okay, what's a period? What does it determine? Let me go a bit up there. Write it in red, of course. Group, oh no, we've finished group, sorry. Period number. Period number determines the number of shell. Oh, apologies, my pen just fell. We're having a little glitch moment. It determines the number of shells that an element, apologies, that an element contains or has. Use little, what color do you want to use? Green, light green. Such a cute color. There we go. Nice and cool. So, what does this mean? Let's go to the periodic table. Periodic table is basically the little reference that we always need to use. Let's take magnesium, aluminum, and silicon. They're both in the same period. The periods are always sideways. Okay, the periods are the rows and the groups are your columns. No, we can't move this. And then, where do we go? Oh no. Group is already written here. Groups is your column. All right, so we've taken magnesium, aluminum, and what was that? Silicon with 14. Where's the note that I made? There we go. So let's take all of them and configure them. All right, magnesium, aluminum, silicon. Why did I think of phosphorus? Okay, magnesium has 12, aluminum has 13, silicon has 14. If I had to configure this, we already had our magnesium from earlier. Aluminum would be 2, 8, 3. We already configured this. Silicon would be 2, 8, 4. Alright, we've already done configuration at this point. It should come easily and you need to do practice on it. If you don't, you can look back at examples in order to ensure you are practicing, alright? Because it is, it's one of the basic things, and in a lot of things, in a lot of chemistry, you will need to be able to know how to configure. Alright? And we see here, all these have have three shells and are period 3 elements. Alright, so that's also proving this little, it's not a theory, it's just the reality, but we're just proving this statement in a sense, okay? So let's go back to the syllabus point. The first A, B is done. The number of occupied electron shells equal to the period number. Okay, there we go. So we've actually done quite a lot in this video. This is part of the unit 2.1 that I did in an earlier video, and this is 2.2. This is kind of like a mind map, the way I make the notes. I can share them in the YouTube link, in the YouTube link down below, maybe, if you guys need it, in Google Drive possibly. So if you guys want it, let me know and I can do it from the next video on. So thank you guys very much, and next time we'll be doing 2.3, so that's another section done. Thank you, and see you in another video.